CPU shuttling deals with the problem of deciding which of the processes in the ready queue is to be allocated the CPU. There are many different CPU shuttling algorithms. The first one is first come, first served shuttling. It is the simplest CPU shuttling algorithm. The process that requires the CPU first is allocated the CPU first. The implementation of the first come, first served policy is easily managed with a FIFO queue. When a process enters the ready queue, its process control block is linked to the tail of the queue. Let's look at an example. Consider the following set of processes that arrive at time 0, with the length of CPU burst time given in milliseconds. So we have 3 processes, P1, P2, P3. The Gantt chart for the shuttling using first come, first served is, you can see the Gantt chart. You must grab, you must draw it. Okay, because P1 first come, so it is allocated CPU first. So from time 0, and its CPU burst time is 24, so till 24. P1 first is execution and terminates, leave the system. Then we schedule P2 because it is the second in the FIFO queue, and its burst time is 3, so till from 24 till 27, P2 will finish execution and leaves system. Then we allocated the CPU to P3 because its burst time is 3, so from 27 till 30, P3 will finish its execution and terminates. Okay, so average turnaround time. What is the turnaround time? We use the finished time minus the arriving time. We get the turnaround time. So for P1, its turnaround time is 24. For P2, its turnaround time is 27 because all processes arrive at time 0. For P3, its turnaround time is 30. Then we plus them all together and divide it by 3, we get it the average turnaround time. About the waiting time, what is the waiting time? We use the turnaround time minus the burst time. Burst time, we get waiting time. So as for P1, its waiting time is 0. As for P2, we use turnaround time 27 minus its burst time 3, we get 24. And as for P3, we use its turnaround time 30 minus its burst time 3, we get 27. We add 3 waiting time together and divide them by 3, we get the average waiting time. It's 17. So the average waiting time under the first come, first served policy is quite long. Now, the first come, first served shuttling algorithm is non-preemptive. The process keeps the CPU until it terminates or requires I/O. Of course, in our example, there is no I/O requirement, so all the process keeps the CPU till it terminates. Okay. Troublesome for this algorithm is troublesome for time-sharing system. It is important that each user get a share of the CPU at regular intervals in time-sharing system. So this algorithm, first come, first serve, isn't suitable for time-sharing system. Suppose that the processes arrive in the order P2, P3, P1. Then the Gantt chart for the first come, first serve sharding algorithm is this one. So we get the average waiting time is 3, much better than previous case, than this circumstance. Okay, so in addition, consider the performance of first come, first serve sharding in a dynamic situation. Assume we have one CPU bound process and many I/O bound processes. As the processes flow around the system, the following scenario may result. The CPU-bound process will get and hold the CPU. During the time, all the other processes will finish their I/O and will move into the ready queue, waiting for the CPU. While the processes wait in the ready queue, the I/O devices are idle. Eventually, the CPU-bound process finishes its CPU burst and moves to an I/O device. All the I/O bound processes which have short CPU bursts execute quickly and move back to the I/O queues. At this point, the CPU sits idle. The CPU bound process will then move back to the ready queue and be allocated CPU. Again, all the I/O processes end up waiting in the ready queue until the CPU bound process is done. This is convoy effect as all the other processes wait for the one big process to get off the CPU. This effect results in lower CPU and device utilization than might be possible if the shorter processes were allowed to go first.